We now join our lecture already in progress. One thing we talked about was the inverse functions, x cubed and cube root of x. It was very interesting, as we observed, that these graphs have a special relationship such that every ordered pair on one graph has the opposite ordered pair on the other graph. You can see that very clearly by the examples 327 and 27.3, -4, -64, and -64, -4. If you are interested in this concept of inverses, stay tuned, because we'll talk more about that in Unit 3 of this class. Here we're talking about the greatest integer function, a piecewise function with infinite pieces. The graph looks like a staircase. It's quite interesting. What this function does is it leaves integers alone. For instance, when I plug in 0, 3, or -12, it doesn't touch them at all. Not like the absolute value function, which makes things positive. Let's see what happens when we plug in other values. These other values will get rounded down, everyone, when we plug them in. So, when I plug in 4.9, it gets rounded, but it doesn't get rounded like we usually round 4.9. What does it get rounded to? 4. It gets rounded down. But sometimes even better than down, the way I like to tell people about it is think about it this way. It gets rounded left on the number line to the next integer. This is especially useful when you start plugging negative numbers in there, because this can really mess with people's heads. Because if I plug in a number, -3.2 in there, some people get very confused about what that should get rounded to. But this always rounds non-integers down. So if you think of the number line, here's 0, here's -3, here's -4, and right here is -3.2. It's quite clear where it gets rounded to, because it always gets rounded down to the left on the number line. So this actually becomes what, everyone? -4. And you can see why that might mess with some people, because when you're dealing with positive numbers, it's very, very easy to see what's down or to the left. But when you're dealing with negative numbers, it can be a little bit trickier to understand. So if I put in -1.1, what does that get rounded to, everyone? -2. Because it always goes left on the number line to the next integer. Unless you just put it in an integer, then it leaves it alone. In case anyone's curious, there are some textbooks you will see that will call this the floor function. That is another name. Actually, that's how I first learned it, was the floor function. And they use slightly different notation for it, where they just take brackets and they just chop the top off of them. So if you ever see that in a textbook, or someone starts saying, this is also called the floor function, they're actually right. And in case you're curious, there is something also called the ceiling function that rounds things up, but we don't do that in this class. Yeah, question?
Was the range on this guy also -infinity to infinity?
It's not -infinity to infinity because only integers can come out. So even though the integers could be as small as you want or as large as you want, they're still just integers. So we cannot write them in interval notation. What we have to do is we have to write a list that indicates every single just integer. In other words, 0, 1, 2, 3, 4, 5, ... and -1, -2, -3, -4, ...
Okay.
Because yes, the number you get out can be as small as you want or as big as you want, but it can only be an integer. And when you write interval notation, that kind of implies that you can have any decimal or fraction in there as well. And that does not work for the range, only the domain on this one. Good question. Any other questions on that one? Okay. So let's talk about our basic functions again. Let me just summon them up here. Copy. All right. Here are our 5 basic functions. Now, what we're going to do is we're going to work with these 5 basic functions in section 2.7, and we're going to do some things with them. But in order to work with them, it's not just enough to know the equation that goes with the graph. It really, really helps to know some ordered pairs on the graph. And I don't just mean any ordered pairs. I don't mean just go ahead and plug in several x values and get several y values. I mean ordered pairs that really give you the representative shape of the graph. For instance, f of x equals x squared. Yes, I could just plug 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 into that and get 10 ordered pairs, or actually 11 if I did that, 11 ordered pairs. But it is better to plug in ordered pairs on both sides of the y-axis. That way, you actually get several ordered pairs that really show the shape of the graph, not just maybe one half of the graph. And it's also good, and I know I'm asking a lot of you, but it is a math class, it is also good to be able to list those ordered pairs left to right. In other words, the x values get larger as you go. Because it's a nice, clean way to do it. It's a good way to remember the 5 ordered pairs. And I admit, and you all know, that there's an infinite number of ordered pairs on this graph. But whenever we draw a graph that we don't know that much about, we always start by just plotting some points and then kind of connecting the dots. We don't plot every single ordered pair. All right, so can we do that for some more? Yes, I'm going to purposely skip square root of x for now, so I'm not making a mistake, everyone. Absolute value of x, I could list some ordered pairs like negative 2, 2, negative 1, 1, 0, 0, 1, 1, 2, 2. And that's not just any 5 ordered pairs, that's 5 ordered pairs that give me a representative shape of what the graph looks like. Same thing with our x cubed and our cube root function. X cubed, we're going to do negative 2, negative 8, negative 1, negative 1, 0, 0, 1, 1, and 2, 8. And that doesn't just tell us one part of the story, that tells us the entire story. Well, not the entire story, but enough that we see the general shape of the graph. By the way, what was that magic word I used before to describe the relationship between x cubed and cube root? Inverses. Because every single ordered pair on one is on the other one, but swapped. So, negative 8, negative 2. And that's the only one where you can really see it until we get to the end here, because when I'm swapping the negative 1 and the negative 1, the 0 and the 0, the 1 and the 1, you can't really tell. But that one gets swapped also at the end. And that gives us not just any 5 ordered pairs, but 5 representing the shape. One thing that's important is I'm picking ordered pairs that are near the origin, so they're easy to graph. I am picking nice, clean numbers. I could plug some nasty decimals into here, but why would I do that? And I'm also making sure I'm picking numbers on both sides of the y-axis. It's very, very easy to get into the habit of just maybe plugging positive numbers into a function. But if you plug just positive in, you're missing out on maybe half the graph, and you don't know what's going on with the other half of the graph. Everyone cool with that? Now, there is one of these functions up here that we can't pick things on both sides of the y-axis because the graph doesn't exist to the left of the y-axis. So when we look at the square root graph, I can still go left to right, but this one I start with 0, 0, because that's the farthest left this graph goes. And then I just pick numbers that I know the square root of. Like 1, square root of 1 is 1, square root of 4 is 2, square root of 9 is 3, square root of 16 is 4. And that's enough to give me the shape of the graph. So for the exercises we're going to be doing today, class, it is a very, very helpful thing to, when you see one of these 5 functions, x squared, absolute value, x cubed, cube root, square root, when you see one of these 5 functions, to not only get a picture in your head of what the graph looks like, but to also be able to list some ordered pairs from left to right that give a good representation of the shape of the graph. And you'll see why that's so important with the examples we do today. This isn't just going to be me telling you that's important, trust me. It's more like me telling you, this is important, trust me for a few minutes, I'll get to it. Okay, so I do not expect you to have all these memorized right now, but I do expect you to start learning them because it will really help you out later. Let's move on. What are we going to do with the 5 basic functions that we just saw on the previous page? What are we going to do with them? We're going to do transformations. We're going to move the graphs around. And I prepared a picture to show you what I mean by that. Let's see if this one takes up an obscene amount of room also. So transformations, right there, copy, edit, paste. Yeah, that's big. All right, we'll scroll down. The first thing we might see is we might see a graph get moved up or down from its original position. That's called a vertical shift. The way that might happen, and all this will make more sense as we go, is you might add or subtract a number from the function. And what that will do is it will move the graph up or down. So if you take that original absolute value function and you add something to the end of it, you're going to move the graph up. If you subtract something from the end of it, you're going to move that graph down. Vertical shift. That's one way we're going to change those 5 basic functions. And if we can do a vertical shift, we can also do a horizontal shift. That would look more like this. And I'll tell you, class, it might look like I got my plus and minus backwards there, but I have not. I don't remember if the pre-work covers this little detail, but I think it does. But yes, when I'm shifting to the left, I did mean to write a +2 there. When I'm shifting to the right, I did mean to write a -2 there, even though that might seem counterintuitive. But you'll notice, and we'll talk about this in more detail as today's lecture moves on, what you will notice is it makes a difference where I'm adding the subtracting the number. If I'm doing it after the entire function, or if I'm doing it inside right next to the x. And we will talk about that in detail. I'm not asking you to understand everything I'm saying right now, I'm asking you to get ready to understand it. So we can do a horizontal shift. What else can we do? We can do a reflection. We can take one of our graphs and we can reflect it over one of the axes. So you could do something like this. And that's done by multiplying by -1 in the appropriate spot, which kind of looks like you just threw a negative sign in the equation. That will do a reflection if you throw a negative sign into the equation. And then the last thing we're going to do in this class is we're going to do vertical stretching and shrinking. And the way you might do a vertical stretch or shrink is by multiplying the entire function by some number. And that will distort the graph. This is a preview, everyone. This is like the coming attraction of what we're doing today. I didn't just teach you these 4 things. I told you what I'm going to teach you here in a few minutes. So don't be looking at this saying, I can't believe how fast you went through that. I don't understand what just happened. This is what we're going to discuss today in class. And we're going to spend some time on it because it's tricky. But these are the 4 ways we're going to change functions. Vertical shifting, horizontal shifting, reflection, and a vertical stretch or shrink. A couple comments I want to make about this is this. There is also horizontal stretching and shrinking, but not in Math 121, the class you're in right now. So if you're getting help later, from I don't know, your grandma or your sister who's taken this math class before, and they're saying, well, don't you need to do horizontal stretching and shrinking also? You can say, that is a thing, I know that, but that's not something I do in this class. What happens, though, everyone, when we do this is a transformation moves the graph and every ordered pair on the graph may move too. So what we're going to do, for the most part, everyone, is we are going to track how these graphs move by tracking what happens to some of its ordered pairs. That's why we need to know some ordered pairs on the graph when we begin, so we can track what happens to those ordered pairs on our end result graph. What happens to those ordered pairs when we shift the graph left and shift it up and reflect it over and then stretch it? What's going to happen to those original ordered pairs that we know are on the original graph? That's what we need to figure out. That's how we're going to do these problems. How do you know when a transformation has taken place? You're going to see a modified function. A modified basic function. Now here's the cool thing, everyone. For this lesson, we are working with just 5 basic functions. X squared, square root of x, absolute value of x, x cubed, and the cube root of x. Now all of these have something unique about them. There's only one that has a power of 2, there's only one that has a square root, there's only one that has absolute value, there's only one with a power of 3, and there's only one that has a cube root. So we can tell when one of those functions has been modified by looking at the modified function. Check it out. Here's a modified function. Now, whether you know what's going on here entirely, that we haven't covered yet. But can we tell which one of the 5 basic functions I started with? Yeah, because this has absolute value in it. And how many of our basic functions have absolute value? Just the one. So this is a modified version of this absolute value function. Is it pretty clear which function I modified here? Yeah, because there's a squared on it. There's a power of 2. All of our original 5 basic functions, only one has a power of 2 on it. So I have modified this function. So when you see a modified function, the first job you want to do is you want to say, which one of my 5 basic functions has been modified? And that's not so bad. You just look for the telltale sign. Because you see, every change to the original basic function causes a transformation to the original graph and its ordered pairs. Anything that I might put in there is going to change. It's going to cause one of those things to happen that we talked about. A horizontal shift, a vertical shift, a reflection, a stretch, a shrink. Everything that I include, everything that's different from the original function causes one of those things to happen. So when I write this function up here, which I'm writing big on purpose so I can write around it, when I write this up here, we can look at that and say, Steve is messing around with the square root function. That's the basic function he's starting with. But every one of these things, this negative sign, this 5, this negative sign, this plus 2, and this minus 3, all of those things that I've put in here that were not in the original cause one of those transformations to happen. I'll tell you right now what they are, and then we'll learn how I know this, and then you'll know it too. This negative in front actually causes a reflection over the x-axis. That's what makes the whole graph flip over the x-axis. This 5 actually causes a vertical stretch by a factor of 5. This minus sign right here causes a reflection over the y-axis. This plus 2 is going to shift the graph 2 units left. And the minus 3 on the outside is going to shift the graph 3 units down. And if you come with me on this mathematical journey today, I'm going to show you how you can look at a function like this nasty looking function, and you can recognize all these things as well. Because most people, myself included, if they were presented with this function, just, on the street math, and someone said graph it, they'd say, where's my calculator? But I'm going to show you how you can actually do it without a calculator. It's pretty cool. All right, so now we actually have to get into it.
Oh, can you leave that for 2 seconds?
Yeah, what was the parent function here, by the way, everyone? Yeah, the square root function. Parent function or basic function. I do sometimes like to use the term parent function, like the original function we started with. In this case, it would be the square root of x. It's not hard to recognize that parent function because there's only 5 of them you got to worry about. All right. I'll post this right after class if you don't get all of it. Okay. Let us start with the vertical shift. It's actually the most straightforward one. Vertical shift. If a number is added or subtracted at the end of the function, and another way I'm going to describe that is saying outside the function. That will make more sense as you see more examples. At the end or outside the function, the graph will shift up or down. That's how you shift a graph up or down. The ordered pairs from the original or parent function will have a number added to or subtracted from the y value. Now I wanted this to be in your notes so you'd have it so you can look at it. But this actually isn't as bad as it sounds. It just gets very wordy to describe what's happening. Symbolically, what we're going to be doing, everyone, is we're going to take a function, and at the very end of it, we're going to either add or subtract a number. So what will this look like? Well, you take f of x equals the square root of x, for instance. This original function has several ordered pairs, including 0, 0, 1, 1, and 4, 2. That will be enough to make my point. Those are 3 ordered pairs that happen to be on that graph. If we choose to put a plus 3 at the end of the function, what I meant by outside, you can see that now, it's outside the square root to the very end. That's going to shift the whole graph up 3 units. What that means you're going to do is you're going to get these 3 new ordered pairs on the graph, which I get by doing exactly what I said I was going to do, which was I added 3 to the y values. That's going to take the entire graph of the square root function and shift it up 3 units. The whole graph shifts up 3 units. That's how you visualize it. The way you find out what's under the hood, the mechanics of what's going on there, is you add 3 to each of your y values. If someone gave you this, square root of x minus 4, then you would take your original ordered pairs, and instead of adding 3 to all the y values, you'd subtract 4. And what that will do is it will take the entire graph and shift it down 4 units. That's how you do a vertical shift. Just add or subtract the number at the end. Adjust your y values to show that it's either been moved up or down, and you vertically shifted a graph. Unfortunately, that's the one that's the most straightforward. But the other ones aren't so bad. We just need to learn the tricks. Okay, that's how we do a vertical shift. Next, we'll see how to do a horizontal shift. And this is when things get a little bit tricky. If a number is added or subtracted directly to or from x on the inside, the graph moves left or right that many units. The whole graph will move either left or right instead of up or down. But it is backwards from what you may think. This is not a mathematical trick. This is not something we threw into math to make it more tricky. This is the way it actually works, everyone. The horizontal shift, what you see in the equation, actually does the opposite of what most people would think it would probably do. So, now what we're doing is we are actually putting the number that we're adding or subtracting inside the function right up against the x. Not at the very end, when everything's done, but right up against the x. Graph moves left when you add a number and you subtract from the x values in the ordered pairs. If you add a number, you're actually moving the graph left, which does seem backwards to most people, and you would subtract a value from all the x values in the ordered pairs. If it says minus, the graph moves right, and you add to all the x values. This is how we move a graph left or right. Class, this is a vertical shift right here. That's a vertical shift. Our horizontal shifts look like this. So if our original function is f of x equals x squared, I'm just going to write a couple ordered pairs that are on it. Does everyone see the difference in the horizontal shift, how it's right in there next to the x? It's happening before you square it. With the vertical shift, first you'd square the number, then you'd add 3. With the horizontal shift, first you adjust the number, in this case by subtracting 3, then you square it. It does look different. This is backwards from what you would think it would be. So this says minus 3. So what you do is you're going to the right, and you add to x in all the ordered pairs. Check it out. I am now adding 3 to every x value. And what that does is it takes the entire graph of x squared and it moves it to the right 3 units. If someone adds a number on the inside, you go left and you subtract from x. So with your original ordered pairs up here, the -6, 4, -4, 0, and -2, 4. The entire graph gets moved to the left 4 units. It would look like this. On the outside, you're moving it up or down. And it makes sense. Plus means up, minus means down. On the inside, you're moving it left to right, and it's backwards from what you might think. Plus goes left, minus goes right. If you do not believe me, and you think I'm just making stuff up, that's okay. I probably wouldn't believe me either. You can take one of these new ordered pairs that I'm saying is on it, plug the x value into the function, and you will see you get the y value I'm telling you you're going to get. If you plug -6 in here, what's -6 plus 4, everyone? -2. What's -2 squared? 4, just like I said it would be. Same thing with this one up here with g of x. If we go ahead and plug a 5 in there, 5 minus 3, 2. 2 squared is 4. So it does work. It's just counterintuitive. So check this out. Check this out. Here's a transformed function. What's the original parent function of this h of x I just wrote? What's the parent function? Absolute value. Original absolute value looks like a giant letter V. But this has been transformed. It's been done a horizontal shift and a vertical shift. This right here means it's going to go up 2. What does this mean? Left 5 or right 5? Right 5. That means the new graph for this one would look something like this. The whole graph's been moved up 2 and right 5. See, once we learn these tricks, we can defeat these problems. We just need to make sure we know all the tricks. We doing okay so far? We'll tie it all together when we're done. Don't worry. It's going to be awesome. You'll love it.
Are we going to have a pink bow?
No pink bows in this class. That'd be weird. All right. Reflections are done by multiplying either the entire function. You don't actually multiply the vertical shift, except the vertical shift part at the end. But multiplying the main part of the function by -1, or multiplying x directly by -1. Now I need to say multiplying by -1 because that's really what you're doing, is you're either multiplying the entire function on the outside by -1. So entire function means it's on the outside, and multiplying x directly means it's on the inside. But really what this looks like is, it looks like you've inserted a negative sign. We all know when you multiply anything by -1, you can just do that by putting a negative sign in front of it. You don't need to actually write the 1. So it's just going to look like we inserted a negative sign. So check this out. F of x equals the square root of x, the square root function. Some ordered pairs that appear on that graph are 0, 0, 1, 1, 4, 2, 9, 3. It gives us a beautiful graph. It looks like this. All graphs are beautiful, though. That's one of our basic functions, and I have studied my basic function, so that's why I can just rattle off some ordered pairs that are on it, and that's why I can just draw a quick sketch of it, because I know what it looks like. What someone might do is they might put a negative sign in front of the entire function, like that. Or they might put a negative sign directly in front of the x, not the entire function. Either way, we get a reflection. This one's on the outside. This one's on the inside. This one will make you reflect over the x-axis. But here's the tricky thing. That does make you reflect over the x-axis. But the way you adjust your ordered pairs is you multiply the y values in the ordered pairs by -1. What happens when you put the negative on the outside like that is it will reflect the entire graph over the x-axis. But the way you adjust your ordered pairs is you multiply the y values by -1. But if you do that properly, you will get a graph that looks like this. Reflected over the x-axis, and the way you change the ordered pairs is you multiply them all by -1. And you will get the ordered pairs 0, 0, 1, -1, 4, -2, 9, -3. The whole graph is flipped over. How? By putting a negative sign in front. Over here, just the opposite. Here, you're going to reflect over the y-axis, but you multiply the x values by -1. You do this right, the entire original square root graph will flip over to the other side of the y-axis, and your new ordered pairs for this sucker, just need a little bit more room here, your new ordered pairs will look like this: 0, 0, -1, 1, -4, 2, -9, 3. Remember, it's not necessarily bad to plug a negative number into a square root function if it becomes positive before you take the square root, which is why I can plug a -9 into this function, because if I plug a -9 in here for x, the other negative will turn into a positive 9 before I take the square root. We know that. -9 means positive 9, right? So if the 9 brings a negative with it, and there's a negative waiting for it inside, they cancel, and we end up taking the square root of 9 and getting 3. In case anyone's curious, and I hope you are, I hope you come in here feeling curious, you could put a negative sign in both places. What's that going to do? It's going to do both. There it is. It's reflected over both the x and the y-axis. We did 2 reflections. You can do that. How did I do that? I multiplied every x value and every y value by -1. I could write that here. Okay, that's how we do a reflection, everyone. It all matters where you put the negative sign. Okay, we'll do one last one, then we'll take our break. I know it's time for a break now. I'll still give you the full 10 minutes, but I want to finish our list of things so you can think about them a bit during the break while you're eating your Funyuns. Vertical, stretching, and shrinking. I wouldn't say this is the hardest one. This is just the next one we're doing. If a number other than 1 is multiplying by the function on the outside. So by the outside, everyone, I mean the number multiplying by the function is outside whatever the function is. So not this one. That's on the inside. I mean, we're multiplying by a number on the outside. If a number other than 1 is multiplying by the function on the outside, it causes a stretch or shrink. This actually distorts the graph. If the number is greater than 1, if the number out there is bigger than 1, like 3, 4, 5, 6, 7, that's going to cause what we call a stretch. If the number is between 0 and 1, what's between 0 and 1? Fractions, 1/2, 1/3, 1/4. If the number is between 0 and 1, that causes the shrink. That causes the graph to distort in a different way. if the number is negative, then we also have a reflection over the x-axis. So if the number in front is negative, the negative is actually causing a reflection, and the magnitude of the number is what's causing the stretch or shrink. So if you see a negative 3 in front, we'll see this in one of our examples today. If you see a negative 3 in front, the 3 is causing the stretch, the negative is causing the reflection. It's two things happening at once. So what does this look like? I'll just show you a couple quick examples, then we'll take our break. F of x equals x squared has negative 2, 4, negative 1, 1, 0, 0, 1, 1, 2, 4. You see a new function that looks like this. G of x equals 3x squared. Multiply every y by 3. How do you know that's on the outside? Because this is what it would look like if it was on the inside, everyone. This is what on the inside would look like. There'd be parentheses there, and the 3 would be inside the parentheses before the squaring took place. That's not what we're doing. So this is on the outside. Even though it's right, I've physically written it next to x, that still counts as the outside. This would be what the inside would look like. Multiply every y value by 3, you got it. The entire graph is stretching. And how does that manifest itself in the ordered pairs? By every y value getting multiplied by 3. That's how we do a vertical stretch. It stretches out the entire graph. Maybe the original graph looked something like that. Now, it looks more like this. Stretched out like that. We multiply by 3. This one. Multiply y by 1/2. This is just going to cause it to shrink. Every one of our original y values, so I'm going back to the original ordered pairs, every one of our original y values gets multiplied by 1/2. And so you can see very clearly what's happening here. I'm not going to simplify these. That shrinks the graph. It takes what maybe a graph, the original graph looked like this. And you might think that a shrink looks kind of like a different kind of stretch, but we call it a shrink. So when we come back from break today, we're going to put all these ideas together. That was a long haul. I appreciate you all doing it. Here are some hot tips to help us with these problems. Okay. Every change made on the inside of an original function will alter the x values. So if we're doing something on the inside, that's going to change the x values of every ordered pair. Every change made on the outside of the original will alter the y values. So that's one thing we can use to help us keep track. For instance, everyone, let me show you another large function based off the original parent function, square root of x. Square root of x isn't the most important one, it's just the one I like to work with the most. It's interesting. Here is a parent function, and here is its altered function. So if you've ever sat in a waiting room before, you've probably read Highlights magazine. And Highlights magazine had a feature in there. Well, Goofus and Gallant was actually the best part. But the feature in Highlights magazine I'm talking about was when they showed you two pictures side by side and they said find the differences between the two. Everything that's different between the original function and the new function is going to cause one of those things we just talked about to happen. And the things on the outside are going to change the y values of the ordered pairs, and the things on the inside are going to change the x values of the ordered pairs. So that's kind of nice to remember that. It helps keep more clear in your head. This right here, we're going to subtract 5 from y. That was the vertical shift. What's this plus 4 going to do on the inside? Move it left or subtract 4 from x. Very good. Now, this one's a little bit tricky because it does impact the x's, but the negative on the inside does flip us over the y-axis, but that still changes the x values. So, this is a reflection, and we'll multiply x by -1. Now here's something really cool, everyone. I see a -3 in front. And who remembers what's bizarre about that -3? What's actually going on with that? There's two things happening. The negative causes a reflection. The 3 causes a stretch. So, the neat thing is, even though that's two different things, a negative, which is causing a reflection, the 3 that's causing a stretch, they both impact y. And what we can do is we can reflect and stretch by multiplying y by -3. We can actually do both the reflection and the stretch at the same time, as long as we understand that we're doing two things at once. Because the reflection said multiply all the y values by -1. The stretch said multiply all the y values by 3. Well, multiplying by -1, then multiplying by 3 is the same thing as multiplying by -3. Here's what we're going to do, everyone. We will create a list of ordered pairs for a new function by altering the ordered pairs of the original one step at a time. This will take 4 steps at most. The most we'll have to do is 4 things. Yeah?
Did you say the negative was the reflection or the stretch?
The negative is the reflection, the 3 is the stretch. Maybe I said it wrong, I apologize.
I just didn't catch it.
Yeah, negative is the reflection, 3 is the stretch. Okay. So we're going to create a list of ordered pairs for a new function by altering the ordered pairs of the original function 1 step at a time, and we're going to be able to do this in 4 steps. Now, the only issue we're going to have when we do this, besides remembering all this stuff, is that order that we do things in does make a difference. Now, I need to stress this very carefully. Who has seen this before? Please excuse my dear Aunt Sally. Parentheses, exponents, multiplication, division, addition, subtraction. It's for order of operations. We are not doing order of operations right now. We are doing a different graphing technique called transformations. So we do not use this. I'm not saying this is rubbish. I'm saying we're not using it now. We are doing transformations. And they follow an order that can be slightly counterintuitive to order of operations. But for this technique I'm teaching you to use to graph today, here's what you need to remember. If there is a horizontal shift, you do that first. If the graph is either shifting left or right, that's the first thing you do. If there is a vertical shift, You do that last. That's the last thing you do. That's it for order of transformations. But there'll be a point when you might want to confuse it with this PEMDAS, this order of operations for, plugging a number into a function, but that's not what we're using right now. We're doing a transformation. It's a different kind of technique. And there are some problems that you can do where if you don't follow the 2 rules I gave here, you'll get lucky and you'll get by okay. But there are other problems where if you don't follow these 2 rules, you can get it wrong. But these 2 rules will always help you get it right, so you want to follow them. And finally, an hour and 15 minutes into class, we're ready to do our first big example.
Yay!
Let's do this. So, everyone go ahead and import your grid.
Okay.
And here's our function. H of x equals -2, absolute value of x minus 4, plus 3. First thing we want to identify is our parent function. There's only 5 options. Which one is this? Absolute value. In your mind, right now, hopefully you are picturing that V shape. Now when we move a graph left, right, up, down, reflect it, stretch it, shrink it, it might get a little bit distorted, it might get flipped upside down, but it's still going to keep that basic V shape. There's no way this graph is suddenly going to become the square root graph. It's going to stay that V shape, but maybe it'll look a little different. What we observe, everyone, is we have a -2 in front. We know that's actually 2 transformations, but we know we can take care of them at the same time. We have a -4 on the inside, and we have a +3. We will start by, in any order we want, identifying what each of these things do. Then we'll make sure we actually execute them in the right order. This +3, we are going to do what to the ordered pairs? What to the ordered pairs? We're going to move it up because if it's a +3, and we're going to add to the y values or the x values? Add 3 to y, because it's on the outside. The -4 on the inside, what are we going to do to our ordered pairs?
Move it right.
We're going to move it to the right, so it's the ordered pairs. We will add 4 to, because it's on the inside, good. Add 4 to x. And the -2? On the outside, that's 2 things, but we can take care of it all at once by multiply, what, x or y? Y by -2. Why? Because it's on the outside. Outside is y, inside is x. All right. Now what we do is we write down several ordered pairs that appear on our original function. It is best to do them from left to right and to kind of know which ordered pairs you're working with. So, let's see if I can squeeze these in here. -2, 2, -1, 1, 0, 0, 1, 1, 2, 2. Now I'm not saying it's impossible to draw this graph by just plugging a bunch of x values into this function and getting a bunch of y values out. That can be done. But if we use this transformation technique, the technique I'm teaching you today and I want you to learn, we will not only get 5 ordered pairs on the new graph, but 5 representative ordered pairs that give us the shape of the graph we want. There's a danger that if you plug just 5 numbers into this transformed function, you'll get 5 ordered pairs that are all on the same side of the absolute value. And then you're not going to know exactly what the shape looks like. Right, the order we do these in is horizontal shifts must be first. Vertical shifts must be last. So I guess we'll do this one second. Now, what we do is we keep a running total of our ordered pairs. We do not go back to the beginning each time. I call this, as I said, I call this like a running total. And I will help you. Number 1, the first thing we're going to do to every ordered pair, and the only thing we're going to do to every ordered pair on this step, is we're going to go across and we're going to add 4 to every x value. We are now shifting the graph 4 units to the right. Add 4 to every x value, leave the y values alone. -2 plus 4 is 2, leave 2 alone. -1 plus 4 is 3, leave 1 alone. 0 plus 4, leave the y value alone. 1 plus 4, leave the y value alone. 2 plus 4, leave the y value alone. I have now added 4 to every x, just like I said I was going to. Now, for my next step, what am I going to be doing? I'm going to multiply the y values by -2. Here's something interesting. On this step, am I planning on changing the x values at all? No, so what I sometimes tell people to do is I say, since you're not changing the x values on this step, go ahead and write your x values all the way across. That way you won't accidentally change an x value while you're changing all those y values. Because the x values I've already finished changing on the first step. And remember, I don't go back to my original x values, I keep my x values going throughout the whole thing. Once I change something, it's changed. I don't go back to the originals. So now I'm going to multiply every y by -2. -4, -2, 0, -2, -4. I just multiplied every y value by -2. I have now both stretched and reflected the graph. There is one thing left to do. What is that? Add 3 to y. Are the x's changing on this step? Then lock them in there. Don't accidentally change them, lock them in. Locked, 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 locked. Now I won't accidentally change an x value. And now I'm going to add 3 to every y value. -4 plus 3 is -1. -2 plus 3 is 1. 0 plus 3 is 3. -2 plus 3 is 1. -4 plus 3 is -1. Most people do not walk up to a new function on the street and say, I bet I can get some ordered pairs that I really need if I plug in 2, 3, 4, 5, and 6. That's not generally what people are going to think. Most people are going to say, I'll try 0, 1, 2. But these 5 ordered pairs are going to give us exactly what we need. Check it out. This is awesome. 2, -1. 3, 1. 4, 3. 5, 1. 6, -1. Isn't that smashing?
Totally.
We can now see the shape of the absolute value graph, and like we usually do once we get a general shape, we connect the dots as best we can. And now we have our answer. There are so many cool things about this. The first cool thing is it maintains its shape. Another cool thing is on the original absolute value graph, the original one. This important point at 0, 0 is kind of where everything came together, right? Now look what happened here. Here's 0, 0, right up here. It transformed into 0.43. This point right here, that is still the point where it all comes together. It's awesome. Here's another thing that's cool. Oh, Steve, certainly you can't expect me to believe that you did that correctly. I want proof. Okay, here's your proof. F of x equals -2, x minus 4 plus 3. Someone pick one of these ordered pairs on the bottom row.
2, -1.
2, -1. Okay, watch this. I plug a 2 into this function. Like that. 2 minus 4, -2. Absolute value of -2? 2. -2 times 2 is -4 plus 3 is -1. That means when I plugged in the ordered pair 2, I got -1. Awesome. It works with each of the 5 ordered pairs. This is how we transform a graph, everyone. In case anyone is curious, you can actually see what's happened here. I mean, it looks like it's been reflected. It's flipped over. It looks like it's been stretched. It's narrower than it usually is. It sure has been shifted to the right 4 and up 3. Everything's happened. It's awesome. The other thing you might want to do, and they might ask you to do, is after you're done with the graph, they might want you to make an observation about the domain and range. This graph does go left and right forever still. So the domain is -infinity to infinity. But the range has changed from the original absolute value function because we've transformed it. Now the range is -infinity all the way up to the y value of 3. Do we feel good enough about this to try another one together?
Yes.
Let's do another one. I love them. I think they're cool. Once you know all the rules. But it does take a while to learn them all. It does take some practice, and you do have to try some on your own. It's not just enough to watch me do it, you know that. You have to do some practice on your own to become an expert at these. Anyone can do it though. If you're willing to try, you can do this. I know this guy. This is f of x equals the square root of x transformed. This is what the original function looks like. By the way, if you're keeping notes, I'm sorry, I should have said this before I started writing. I purposely did leave a space in here so I could write whatever was happening. This one's actually going to have 4 things that happen. How do I know that? Just by glancing at it. -3 in front, the negative on the inside, the 3 there, and the 2 there. 4 things are going to happen. I said when you do these things, when you alter the ordered pairs, you're going to have at most 4 steps. Here's an example that's going to take 4 steps. Now you can write down in any order you want what each step is going to do. You just need to make sure you execute them in the proper order. For instance, I'm going to add 2 to y. Why? Because there's a +2 on the outside. I'm going to multiply y by -3. Why? Because the entire function is getting multiplied by -3, so that means I multiply the y values by -3. I'm going to multiply x by -1. Why? Because there's a negative in front of the x. What else am I going to do?
Shift it left 3.
Shift it left 3, which means I'm going to subtract 3. Darn this. Subtract 3 from x. We have to remember that horizontal shift is counterintuitive. It's backwards. How would you catch that if you made a mistake? Well, unfortunately, the way you would catch it is when you got to the end and you checked your ordered pairs, you would find out that none of them worked. So you will catch it at the very end if you check some ordered pairs, but just try to remember it on this step so you don't have to go through and do the problem again. All right, to do this, I'm going to need several ordered pairs for my original function. It's best to list them from left to right, so I'll go 0, 0. Square root of 1 is 1. Square root of 4 is 2. Square root of 9 is 3. Don't really want to go much higher than that because I won't be able to fit it on my coordinate system. It only goes to 10 in each direction. All right, I got to do these in the right order. Which one do I have to do first?
Inside.
Not just the inside, but which one do I have to do first on the inside?
X.
Both insides are x. What did I say? Horizontal shift first, vertical shift last. Sound familiar? Horizontal shift first, vertical shift last. These other 2 steps, the multiplying the y by the -3 and the multiplying the x by -1, you can actually do those in either order. It does not make a difference at all. But I like to finish with the x's before I move on to the y's. Now what we need to do is we need to be very careful and change these ordered pairs. The first thing I'm going to do is I'm going to subtract 3 from every x. Am I going to change the y values on this step?
No.
No, so I think I'll lock the y values in. I don't want to accidentally change them on this step, so I write them in early. Then I proceed to subtract 3 from every x value. I'm getting 4 new ordered pairs. I am on my way. -3, -2, 1, 6. You know, I'm not really on my way if you're not on your way. So, all right, so next step, we're going to multiply the x's by -1. We still are not changing the y's on this step, so I'm going to go ahead and lock the y's in again, because I don't want to accidentally change a number I don't mean to change. And then I'm going to multiply all the x values by -1. That just means if they're negative, make them positive. If they're positive, make them negative. So now it's going to be 3, 2, -1, -6. For the last 2 steps, the x values aren't going to change. I'm just going to change the y values now. So I'm going to lock in my x values. And you know, if I wanted to, I could actually lock them in for the next 2 steps, because they're done. And now, in the proper order, I need to multiply the y values by -3, and then do the last step. So first I'm going to multiply all the y values by -3. 0 times -3 is still 0. 1 times -3 is -3. 2 times -3 is -6. 3 times -3 is -9. That's both the reflection and the stretching step. The last step is the vertical shift. Vertical shift always comes last. I'm going to add 2 to every y. 0 plus 2, -3 plus 2, -6 plus 2, and -9 plus 2. I'm not saying every time you do a problem, because this would get very, very tedious, but it is not a bad idea to check your work. How do you check your work? You take the original function, what was it? What did I call it? G of x, sorry. You take the original function, g of x, equals -3, -x plus 3 plus 2, and you plug one of your new x values into it, and you see if you get the right y value. What x value do you want to plug in there? 2? Okay. Plug a 2 in there. I don't know, let's see here. -2 plus 3 is 1. The square root of 1, everyone, is 1. -3 times 1 is -3. -3 plus 2 is -1. It does work. Also remember, your graph should not drastically change shape. This should not suddenly become the absolute value graph. This is a square root graph. It will still be a square root graph. It will just be a transformed one. So 3, 2, 2, -1, -1, 4. I'm sorry, -1, -4. Good. Almost blew the whole thing. -6, -7. Now this is interesting, everyone. When I did the absolute value graph, I got that V shape, and I just put an arrow on each end to show the absolute value graph went on forever. Does the square root graph go forever in both directions, or just one?
Just one.
Just one. But look at this. Where does the graph stop? Where's this solid point on the square root graph? What ordered pair is that? 0, 0. What ordered pair did 0, 0 become? 3, 2. That's the new stopping point. 3, 2. The other direction is where the arrow goes. The arrow will be at that end. The arrow will be at that end. This thing is stretched quite a bit. And there it is. Domain and range. Well, the secret to the domain and range is actually this ordered pair right here, 3, 2. Because does this graph go left forever? Yeah, but what x value does it get to? 3. This graph also goes down forever, but it gets up to the y value of 2. It's amazing, it's wonderful. It's so cool. It is such a cool technique. And not only will you be learning this technique when you practice these, but you'll be becoming more and more familiar with your basic functions, with the ordered pairs that are on the basic functions. And you just get to practice a ton of arithmetic also. Okay. We cool, class? Much like piecewise functions, at this point, most people say, I think I'd be more cool if you did a few more examples of that. I do not have time to do a few more examples of this. I'm a busy person. No, I would love to do more examples, but then we won't cover other stuff that's also tricky in this class. So, on D2L, there's a link to YouTube with 5 more examples of this, of taking one of the basic functions and transforming it by transforming the individual ordered pairs. You want to see more? You want to see more examples? Those videos will show you the more examples you need. Now, most people don't like this, but it's better than me telling you this now than telling it to you 5 minutes before the exam. You will need to do one of these on the exam. And here's the problem. For the most part, in this class, for the most part, doing the homework is a really good way to practice this stuff and get ready for the exam. I do strongly encourage everyone to do their homework, not just for the grade, but to learn this material as well. However, if you've done some graphing on the homework, you know that the graphing is a joke as far as helping you actually draw a graph. Because you click a few buttons that say, I want my graph right here, and I want you to shift it over there, and now I'm done. And it will do it all for you. So, you need to practice the graphing by hand. Maybe when you're doing your homework, before you type in the computer and have it draw the graph for you, you try to sketch it on your own first to see how close you get to the one the computer draws for you. That's a good thing to do. There is also a worksheet with answer key. It's amazing how clear some of this stuff can look after you watched a few examples and how you think I got this. And then some of you are taking a test and you're sitting there, pencil and paper, with no narration from a loud person in front, and you've got to graph these things from scratch. You have to practice them on your own. And the homework, even if you get 100% on the homework for section 2.7, that's not going to give you the graphing practice you need unless you try some of it by hand. So please, 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 make sure you are practicing graphing these by hand as well as getting a good grade on the homework. We cool with that? All right. Of course, I'll remind you of this again, that you're going to have to do one of these on the exam when I give you the study guide next week. That will be on there, but just want to tell you now. Because for the most part, the homework is awesome prep, but not for graphing, unfortunately. Why do we use the ordered pairs we use? Well, they represent the shape of the graph. Using those 4 or 5 ordered pairs gives us a good picture of what the graph looks like. They're nice numbers. And they're close to the origin. You know, f of x equals the absolute value of x has this ordered pair on it. That's absolutely true. That ordered pair is on that graph. Anyone feel like plotting that point? Anyone feel like drawing a coordinate system that goes up to 1,000 so you can fit that one on there? I don't. So we stay close to the origin. Anyone feel like manipulating that ordered pair, 1.736, 1.736? I don't. It's near the origin. It's on this graph, but we don't use it because it's a sloppy mess. It's not nice numbers to use. So the reason we use the ones we use is because they're nice numbers near the origin that give us a representative shape of the graph. That's why we use the ones we use. It wasn't just 5 that we picked out of a hat. And as you know, if you just chose to do this, is that really going to show you what the graph of absolute value looks like? No, if you just plot those, it's just going to look like a line. So that's why we need to represent the shape of the graph. All right. The other thing that will really help you keep your work organized when you do this type of problem is try to keep ordered pairs of originals left to right. Now, if you do a reflection, it will obviously mess with your ordered pairs, but you try to keep the originals left to right. For the absolute value function, it is not wrong. It is not wrong to say these are the ordered pairs on the absolute value function. Because I absolutely do think that those, and they are, those are 5 ordered pairs on the absolute value function. But if you plot those, you're going to be all over the place. And you might still get a right answer. You might do just fine. What I'm talking about right now is not the difference between right and wrong. I'm talking about the difference between keeping your work organized or disorganized. This is not going to go nearly as smoothly for you when you do these types of problems. As that will. And once again, that's not required to get the right answer, but I think it will help. And if you look back at my notes, how I listed them, you will see that I did always list them from left to right. In fact, let me just insert that into your notes right here. Yes. Oops. Copy. That way you have it in these notes too. I put this on the board earlier, I think last class, but now you can see the 5 ordered pairs for each one, labeled order from left to right. And now that's in your notes, so you can look at it later. All right. A couple more things to cool down today. Altering just one ordered pair with a basic function or mystery function. Huh? You didn't know there was going to be a good mystery today. All right, now, we'll do absolute value again, because we're here. And check this out. Now, I'm not saying that's one you want to plot, because it's getting kind of far away from the origin as far as drawing a coordinate system goes, but does everyone agree that negative 12, 12 is on that graph? Here's the question. What ordered pair does this become on g of x? Now this is exactly like what we were doing before, except we don't need to worry about drawing the graph, and we only need to do it with one ordered pair. This is what we did, though, on those graphing problems. We took a bunch of ordered pairs, we did a bunch of things to them, and then looked at what we had and graphed them. This time we're just going to change one ordered pair. It's actually a faster problem. But it still helps us practice identifying what each one of these things does to the ordered pair. Multiply y by 2. Subtract 5 from y. How come I know both of those are y? They're on the outside. Subtract 1 from x. Multiply x by negative 1. Does order make a difference?
Yes.
Yeah, it does. What do we always do first?
X.
Not just x, but what part of x? The shift or the reflection?
Shift.
The shift comes first. Vertical shift comes last. The other two can really truly be done in any order, but I like to finish with x before I move on to y. So now what we do, everyone, is we take negative 12, 12, and we run it through those 4 steps. And we get a brand new ordered pair. You want to try it on your own? Go ahead and give that a try. See if you can do those 4 things to that ordered pair and get me a brand new ordered pair at the end. A nice shiny one for Steve. Make sure you do it in the proper order. Make sure you always work off the one you just did. You don't go back to the beginning each time. You just keep working off the one you did. Oops. There we go. You should end up with 1319. Now, you could do that with as many ordered pairs as you want and draw the graph. This is the exact same process we did before, except we're not drawing the graph. And I can pick any ordered pair I want because we didn't need to worry about plotting it. And sure enough, everyone, I promise you, that if you plug 13 into that original function, into the transformed function, it will simplify to 19. All right. I know I'm low on time, but I still have time to do a couple more quick things here. What did I say? Did I say there were mystery functions also? Look at this. F of x has the ordered pair -5, 7. I don't know what that function is, f of x. I just know it has that ordered pair. But what does this one have? It's also the same process we did before, except now we just don't know what the function is. But can we still identify that there's a horizontal shift and a vertical shift here? Yeah, I can see that this -2 is on the inside. So I can see that I add 2 to x. I can see this +3 on the outside. I can see that I add 3 to y. Whatever this new one is, it has a horizontal shift and a vertical shift that's going to spit out -3, 10. Done. I can't check my work on this one because I don't know what the actual function is. But I still can say, if we start with this ordered pair and we have this type of transformation happening, a vertical shift and a horizontal shift, this is what I'm going to end up with. Every now and then you'll encounter a mystery function. What else can happen? Look at this, he said, still with 2.5 minutes to go. F of x equals x cubed. F of x gets shifted left 2 units, reflected over the y-axis, and shifted down 5 units to get g of x. The question is, what does g of x look like if we do those 3 things? Now, first and foremost, g of x is another cubic function, another third power function. So I start by doing this. The graph was shifted left 2 units. Do I know how to put a shift in of left 2 units? Is that a +2 or a -2? Where? Inside or outside? Inside. Got it. Reflected over the y-axis. This is tricky, everyone. When you reflect over the y-axis, you change the x values. It actually says that earlier in your notes. You can verify that later. So if we're changing the x values, where does the minus sign go, on the inside or the outside? Inside. And then finally, the easiest one, I think, shifted down 5 units. What do we put and where do we put it? -5 on the outside. Class, what we will start with next time, because we are not done with this section, if you'll just give me another 10 seconds here to tell you, we are pretty much done, but just give me 10 seconds here. We will go from transformed graph to equation. We'll do that next time. And we'll also talk more about even and odd. So when you're doing your homework for 2.7, you notice that there's some even and odd functions. And then you're like, did Steve go over that? I did a little bit last time, but I have some more to do with it. But I am out of time. Ooh, just now.